right, welcome everyone. Welcome to today's our seminar. We have Andreas Adelman today. Dr. Adelman is the first Hours Fellow, and he received the fellowship in 2001. Dr. Adelman now is a senior scientist and head of the Interdisciplinary Laboratory for Science, Scientific Computing and Modeling, with close to 30 scientists at the Paul Scherrer Institute in Switzerland. He also teaches courses at ETH. He teaches courses in accelerator modeling, computational physics, and leads a seminar on computational physics. He got his PhD in applied math from ETH Zurich. His research interests include advanced accelerator concepts, nonlinear dynamics, large-scale optimization, and machine learning. In 2012, together with researchers from ETH Zurich and IBM Research Zurich, he received the PRAISE Award, which recognizes a breakthrough in science achieved with high-performance computing resources in the area of reduced-order modeling and optimization. With that, I would like to welcome Dr. Adelman. Andreas, the virtual stage is all yours now.
Thank you, Jackie. Thank you very much for having me here. So my plan is to tell you short stories, I guess, today. This will be not rigorous. So if you're looking for proofs today, you better switch off. The plan is to give you first a kind of a personal account, so where I came from, what my path is, then of course the relation to the Alvarez Fellow, very important relation, and then I guess I come to 4 main courses, and well, then it's probably around 8 o'clock here, and then I'm hungry, so then I will stop and go for dinner. So I will start with some kind of a personal, so my way, because I think it's interesting. It's not the usual. It's not the usual one where you go to high school, college, and then you do PhD. So I really first start an apprenticeship and was working kind of a shop and repaired radios and television. So it's something that you can do, this apprenticeship system, especially in Germany, in Switzerland, Austria. That is another really another route of your education. So after you go for 3 years school, but you're working also in a shop. So if you still have an old radio, television, and you want to fix it, you can send it to me. I'm still kind of equipped to do that. So after that, I went back to school. That was working a day and doing school in the evening. So that's also a kind of a system we have here. And I basically got a degree in electrical engineering and did this kind of stuff here with electrical engineering, but with in-depth computer science education. So there is kind of a mix. So, and after that, well, I thought, well, okay, I did that for maybe 2 years, and I went back to university, and then the idea was really to get a scientist, and you see here nuclear power plant. This will play a role in the stories, and this one here you can hardly read, but that's okay. This is basically logic and pure math, so to say. So how I became a scientist, it basically started during a semester. A project at the university where we had to do projects. I got assigned to PSI and got involved in basically accelerator modeling. And so basically a scientific contribution in REACH, and the scientific contribution in REACH has to do with nuclear power, as we will see in a minute. So that was kind of an internship, you would say today. But then I went back to university and did my diploma thesis. At that point, we called it Diploma Thesis, das relationale Datenbankmodell im Vergleich mit einer abstrakten Informationsalgebra. You see, at this point in time, we even are allowed to write our thesis in German. So the relational database model compared to an abstract information algebra. So that was the title. This has nothing to do with accelerators, as I said before. This was theory and proof type of thing. Was super cool 1 year. And actually, after that, I got a contract at IBM Research to basically doing a PhD in this area. But also, I still kept my title PSI, and a few months later, I also got basically a contract to pursue a PhD related to PSI's high-power accelerators. And that's basically what I did. So I stopped at IBM, went to PSI and did a PhD in applied mathematics, seminar of applied mathematics. And the idea here was a precise numerical three-dimensional model of high-power cyclotron beam dynamics. So usually in an interactive session, we could now start asking what is the memory of society. And why do I ask what is the memory of society? Well, this has to do with nuclear power, and this has to do with the waste of nuclear power. So we have to store the waste of nuclear power for quite some time. I will give you the details on the next slide. Now, we all know this is 100,000 years or several 100,000 years. And if we are now looking back, maybe 3000 BC, we could argue on that. But let's say a couple of thousand years BC, that's what we these days know, find stones, find some paintings and other stuff. So that's the memory of our society. We have to basically put nuclear storage safe away for more than, let's say, 300,000 years. So that's this guy and that's you, right? So nuclear waste is a long memory, and that brought me in. That was the kind of idea I had as a young student. Where can I help society to get rid of the problem? And well, the idea, of course, had Carlo Rubbia, Nobel Prize winner for the W and Z boson discovery. But he came up with the idea to use an accelerator, drive a subcritical reactor, and basically transmute long-lived radioactive isotopes, such that within a couple of generations, this is the toxicity, and this is years, within a couple of generations, let's say 800-900 years, you can put your radioactive waste basically in the backyard. If you do nothing, if you put it in a deep geological storage, well, then you are talking about the 300,000 years I was referring in the slide before. So that was the idea. So I thought, well, okay, high power accelerators, PSI, we have high power accelerators. We use these guys, and then we transmute radioactive waste and even get some power to the grid, but that's secondary. So already during my PhD, when I was basically working on a precise model of these machines, I got in touch with Rob Ryan. He already, during my PhD, invited me to Los Alamos. And at that time, For maybe some of you remember, the US had actually a very nice program to do this, to do exactly this. And at Los Alamos, they had the low energy demonstrator accelerator, LIDA, and that was commissioned. And I did my PhD on modeling these machines. Everything kind of worked out as I was basically planned. Of course, now we all know we do not really have such a system yet. Except in China. In China, they really are serious in building a machine, and the rest of the world is just doing super small demonstrators. So now, after my PhD, and this is Rob Ryan. This is Rob Ryan. This is the old Bebertron building. So that was 2001. You can read that off this website. There's a few nice pictures there. So Rob basically was motivating me to apply for the Alvarez Fellow, and then Horst Simon, he was at that point in time leading this effort, chairing the committee that's selecting this, and both are not only mentors but by now very good friends. So I came to basically be the first Alvarez Fellow. We had a wonderful time with 3 kids in the Bay Area, and very important, these LBL bonds are still going strong. At that point, I also got to know John Jolf. We started with parallel HDF5 things. This is stuff that's still working, that we still use today. And I visited him in June. You see, we took a photo in front of Perlmutter. So I was at Berkeley for a bit more than a year, and then had to decide to go back to BSI for a tenure track position, or still continue going on. Also personal things happened during that time. So we went back with the family to Switzerland. I got a position at PSI, and since then, basically, I'm at PSI and ETH in Zurich. So that's basically the kind of personal background I want to give, to put that a little bit in context. Maybe a biography that is not the usual one. I thought it's maybe interesting to share that with you. So understanding dynamical system or charge particle accelerators, for me, dynamical system is kind of first. The charge particle accelerator is a special dynamical system. So what we usually do, we basically have a transport equation for a phase space, 6-dimensional phase space, time dependent. For sake of simplicity, I'm just assuming here it's non-relativistic. And the electric and the magnetic field in these machines come from external magnets. These external magnets could be something like this, or that's 400 tons of steel, could be something like that one here. So these are electromagnetic field or electrostatic field, depending a little bit in which area you are in, coming in basically here into this B and E fields. So and then, especially these days, collisions now start to play a role in this non-neutral plasma. But what I want to stress here is the multi-scale phenomena. So this is the 1 mile long linear accelerator in Los Alamos. This, for example, is our proton cancer facility at PSI. But if you just look into this machine, the paths that the particles are traveling are basically in order of kilometers. So the spatial scales are from nanomicrometers to kilometers. Velocity scales are from non-relativistic to highly relativistic cases. So that's the kind of dynamical system I'm talking about. Now, method of choice for doing precise simulations is a particle in cell scheme, and this, of course, you all know, is very challenging, not only with the numerical treatment, but also with the computational. Good. So, so these are the dynamical system I'm considering, and if you want to see, the references are at the end. So, for example, this is a kind of line of work where we started in 2012 with a paper for a new experiment using high-power cyclotrons to search for sterile neutrino. With a PhD student, we worked out some quite interesting numerical schemes, also relying on software from Berkeley AMRX, and now a very recent paper where we basically showed some high resolution simulation of a whole facility. So what can you learn if you do this type of simulations? You can learn several things. One is, for example, we are looking in a phase space. This is just a projection from the 6-dimensional phase space. And while the beam is going through these machines, this phase space, for example, gets filamented. So you have a very nice core, but then you get filaments, which is usually non-reversible. And then you have these halo particles. And that's what you are interested in. If you have a megawatt facility and your core is not under control, then your machine looks like a Swiss cheese. It has a lot of holes in, as I show you here. That's basically a collimator that prevents the beam going to some more delicate devices. And if the beam hits such a collimator, it just simply melts away. So understanding dynamical system means, on one hand, understanding the phase space and the dynamics in such a phase space. On the other hand, of course, we want to minimize losses, and we, of course, want to prevent damage. So the challenges involved here, I think I'll make a light on here a little bit. Okay, the challenges involved here are always threefold. You have a computational, usually high performance computational challenge. You have to model physics. So depending in which regime you are, fully relativistic, fully electromagnetic, maybe you are electrostatic, depending on the situation. And you have some non-trivial mathematics to deal with. So collisions is one thing, but for example, noise in particle in cell schemes are non-trivial to grasp from the mathematical point of view. So as a computational scientist, you're always wearing three hats. So my plan now, and that's the basically the four-course menu. I will still all this is now centered or started during my PhD, and then very specifically when I was at Berkeley. So I give you a little bit of history on software engineering consideration, because at the very end I will show you Opal, which is a open source community code. And this software engineering considerations are very, very important. To give you an idea, so Opal at the moment is roughly 1 million lines of C++ code. So, and you will see that the team, it's an international team of roughly 12 people that are working on. Okay, so let's go on with a little bit the context. So Opal will be the last point. I will now start with a library I was developing for the last almost 20 years, I guess, which basically gives us everything we need for PIC, and that's fields and particles. And before discussing this one, I will show you Alpine, then a set of portable plasma physics PIC mini apps for exascale. So when I started with my PhD, remember the idea was to do precise modeling of high power cyclotrons, and at that time we had a program from CERN that was called MAD, Methodological Accelerator Design, and it was version 9. Version 9 was the successor of version 8. Version 8 was Fortran 77. And then they basically converted this old Fortran 77 code to C++. So that was the time where design patterns and all that were coming on. We did a lot of very clever object-oriented design, over-designed, we would say today. But be careful, right? We are 89. So C++ kind of got basically standardized, etc., etc. At the same time, at Los Alamos, they had something they called PUMA, Parallel Object-Oriented Methods and Application. It's basically a framework for particles and fields. PUMA version 1.0, PUMA version 2.0, and then basically PUMA died. The same happened with MAD 9. MAD 9 died because CERN just simply had no C++ knowledge, and the guy who initiated it was retired. So PUMA died, MAD 9 basically died, but in between, during my PhD, I did a marriage between MAD 9 and PUMA. I called it MAD 9P for parallel. So that gave me basically the ability to have a very general accelerator framework from the accelerator physics point of view. So I could basically do linear accelerator, I could do cyclotron, very, very general. That was basically MAD 9, except cyclotron. Couldn't do the cyclotron, so I added that. But I added also parallel capabilities. I added particle and fields, and so I could do space charge or Coulomb interaction. So big n-body problems was taken care of PUMA, and then basically the accelerator part is coming from here. So here was basically my PhD ended here. So I came to Berkeley, and then I started with John Schalf actually to look into particle fields and parallel I/O. So we created on top of HDF5, we created a library we called H5HUT. And that was a very nice performing library for larger scale input-output on the actual machines then. So, and at Berkeley, and then back to PSI, the first Opal release, so that a lot of MAD went into Opal, and a lot of PUMA went into IPPL, independent parallel particle layer. And so this whole thing, so again, in Opal was using IPPL because of the fields and the particles. So, and this whole thing now moved on until today. And I will basically skip this here and now will tell you what are the greatest in this IPPL 2.0 and how Opal is at the moment. So, but one thing you have to see that this is really close to 25 years of software development, and we still have lots of original MAD code in Opal. Of course, we modernized things. You would not really recognize the code itself. But some of the structure are basically survived 25 years. The overall structure survived 25 years. We had to redesign a little bit because, as I told you before, this was the age of design pattern and things were kind of over-designed. So we basically, we were swimming with C++ up to now to the latest features that we are using in this code. So what is IPPL? IPPL today looks basically like this. There is an FFT-based Poisson solver, fields, differential operator, interpolation. There are particles, meshes, load balancing, domain decomposition, orthogonal recursive bisection, communication of buffer factory. Then the FFT is based on Hefty, out of Jack Tongara's kitchen. And to make that all performance portable, we rely on Cocos, and the parallelization we get via MPI. So the goals, before this one here and also Puma, this was just simply MPI. We of course also went with MPI and used one-sided communication, start using one-sided communication and stuff like that. So the goals of the current version is performance portability. We get that with Cocos. We upgraded the code to a minimum C++ 17 standard. That simplified quite a bit this kernel IPPL. So we really could basically go from 90K to 20K lines of code. We kept the expression templates. We'll show you that in a second. And we kept the changes to the user interface a minimum because at some point we want to move in. IPPL 2.0 in Opal. So why Cocos? Well, we did a small study and looked at other performance portable abstraction layers like Alpaca, Trust, and Raja. We basically looked at what type of licenses, how many contributions. I mean, this was basically a while ago when we did this study. And we also looked at memory management and complexity. And after all this and a lot of discussion, we basically went with Cocos, and we didn't so far regret this. Works very well actually. So give you a kind of a glimpse how that looks like. So particles in IPPL are derived from a base class. You get different particle attribute, depends on your problem that you do. So you can, that's kind of a container. You can put stuff in. Then these particles are laid out among your computational resources. And then we have Cocos, the expression templates, and of course communication. If you now, a kind of a particle bunch. So if you have many particles together, will maybe look like this. You have position and velocity, a mass and the charge, and a social security idea, which is inherited. It's always there. And then you would maybe update your position, the position plus the time step times the velocity. And here is the thing. This will compile into one single COCOS kernel. For those who know expression templates, this is basically lazy evaluation in the assignment operator. And this, of course, makes the things you would like. You have one big loop where everything is in. You don't have any temporaries. So these expression templates, of course, comes with a bag of complexity. So, for example, this is the operator of the particle attribute of a particle attribute, and you can add attributes as you wish. So you have to make these things pretty general, and that is one of the most let's say brain intensive part of IPPL. But the nice thing is it avoids the temporary object, as I said before, reduces the number of COCOS kernels, and does lazy evaluation. And you can do these tricks on particles and fields, and that's what you use. That's what you need if you do pick, and supported by these expression templates are the normal operators that you would expect. So how does, let's show you an example that's already from the mini apps. So this is basically a panning trap. So you have a blob of charge in a trap. So they basically just stay there and move slightly. But as you see, the density are different. So you have to basically adapt. You have to basically adapt your grid, and you have to send around particles. And this is just a small thing to show you that devils are in the details. So if you would do it naively, you would look at the runtime in this pie chart, and you would basically see that a particle sends here, particle send, and particle send is basically already killing you. If you do a buffer, so we need to do a buffer factory, especially for these new devices like Amperes, and so all these GPUs with these pre-allocations instead of 5,000 seconds. We can basically do this in 51 seconds. And yeah, that what you want to see, that the solve is taking most of the time. That's what you see, and not a particle send. And basically this yeah, so this pre-allocation is just a small example, and an example that brings me to the involvement of students. We have involvement of students at all levels. Showing up here the work of Michael Ligotti. He did basically a semester project and implemented orthogonal recursive bisection in this IPPL framework with all the COCOS kernel and all that gizmo. So this is all student work, very highly talented students that we have. And what you see here is basically the domain composition of 64 ranks. So these students are involved, especially from the computer science and engineering track at ETH. They have usually very good computing, numerical math, and when they come to me, they are in the physics track. And of course, if you teach at the university, you have students available for doing this type of work. So that's IPPL. It is everything we need for PIC. At the moment, we are using it mostly for electrostatic PIC, but there is a PhD student, Sonali, she's working on a full EM PIC and will then basically add new features to IPPL. Okay, so Alpine is now basically taking IPPL and basically apply it to several standard, let's say, plasma physics applications. The idea here is to exercise performance portability at exascale. Okay, we do PIC, as I said before. Alpine now takes IPPL, as I've shown before, and we have at the moment 3 tests: Landau damping, panning trap, and the two-stream instability. All these full 3D applications are not more than an A4 page of code. So it's really a mini app. You can use this mini app on several architectures. You can compare that with other library if you want. And I just show you one kind of scaling study that we have done a couple of months ago, and this is under review, just to give you an idea when I talk about scaling. So that these are the grid sizes, that's the number of particles. We did some weak scaling runs on Pitt-Stein and also other machines, and this is the only speed up graph that I'm showing you. Showing first here Perlmutter. So we do linear Landau damping, and the solid lines is a 512 cubed grid with 1 billion particles. The dashed lines are 1024 grid with 8 billion particles. So that's basically Perlmutter. That's Perlmutter as well. Still with the old slingshot interconnect, to mention that. And so this is Summit. That's Pitt-Stein. This is Cori. This is Cori, and again here Pitt-Stein. The same code, the same library, just recompiled to go. Performance portable and scalability. So that's the idea. That's the idea. And if you want to see more, there is a paper we have submitted, and it's available on arXiv, where you see a lot of the details on this scale. So now what is OPAL? OPAL is the object-oriented Pole Accelerator library. This is, I could say, the Swiss knife of accelerator modeling, because we can basically do all conventional accelerators, because this is based on this MAD language, very general language to describe accelerators. OPAL is built up from the ground as an HPC application, and it runs on the laptop and on all the other machines, so to say. Very important, we have a very active developer team that started all at PSI and now getting kind of a little bit of recognition. These are the different institutions that are participating in this open source enterprise. So I think this is also quite interesting. If you start with a new code, if you start with a new very general code, of course you know this. Maybe I knew this later on, but no one is waiting for you, right? Whatever you do these days, no one is really waiting for you. If you are into software and stuff, this is a nice book from Geoffrey Moore. He's an organization theoretician. So he is looking how to organize things and stuff like that. And he came up with this technology adoption life cycle, right? And this is kind of universal. When you start with something, when you bring something in science or wherever, you have the early, you have the innovators, right? And the guys who have always want to have the new stuff, and then you have early adopters, and then you have basically a gap. And crossing this gap to go into early, into basically a majority of users. This is sometimes very, very time consuming and frustrating. So the area under this curve basically represents the number of users. And so we struggled with Opal quite a couple of years, probably in the order of 10 years, to basically cross this chasm here. I'm happy to say that we are here. So we have roughly 100 users all over the world, including the developers, which of course are always users in such enterprises. So I show you one more example. This is from the AWA. So this is the Argonne Wakefield Accelerator. That was a proof of principle experiment regarding electron cooling. So what you have here is an injector, linear accelerator, and you have here a wiggler where basically you put these electrons on a roller coaster and they radiate, they emit light, and we could do a very, very nice experiment. So you see orange and red are experimental data with and without a wiggle, and then we have here the simulation, the Opal simulation. So from the picture norm, that kind of looked kind of well resolved. Some of the features are really present. What is even more important, that I think this is one of, or maybe the unique machine where the unique accelerator framework where you can do a full start-to-end simulation, including radiation. So here we are doing electrostatic, here we are doing full electromagnetic, and then we are switching back to electrostatic. So we not only have these capabilities, but we can basically turn it on and off if you want. So that's my last slide. The Alvarez Fellow was key for my research. It was key. Definitely what I have shown you here today is not the only thing I'm doing, but I selected research that is kind of related to my Alvarez Fellowship. Definitely at Berkeley, things are started. Network were formed and still stable today. A sound software engineering strategy, I think, paid well off. Horst at some point told me this marriage of Puma and this accelerator code from CERN, jumping into the newest software engineering trend at that time, was one of the major points while I got the fellowship. And this strategy basically paid off until now. So with IPPL, you can use this for research within PIC methods. I showed you a couple of things here, but for example, we did PIC and noise. It's a nice paper came out last year. And we basically did everything in IPPL. We didn't do a prototype in MATLAB or Python. We could do everything in IPPL. So the two-language problem, if you use IPPL in PIC, is basically non-existent. Even at the moment, IPPL 2.0 is not yet totally dimension independent. Then I showed you Alpine. So these are many apps targeting exascale architectures, very simple one-pagers running on all these architectures up to hopefully soon the full Perlmutter. I showed scaling up to thousands of GPUs and CPUs and GPUs on these machines, and now we have to do the integration of this new IPPL in Opal. Oh, the real last slide. I have 2 roles to fill in my group, so please, if you know postdocs or if you are a postdoc and you want to spend 2 years in Switzerland, I have an open for basically Opal IPPL and performance portability, and a possibility for Marie Curie fellowship on performance portable PD solvers. Take a photo of this QR code, and you get all the information. Okay, thank you very much. That's all I have today.
Thank you, Andreas. The floor is open for questions. Yes, John.
Andreas's very impressive results. On page 24, you mentioned the pre-allocation strategy could bring up thousands of factors in speed up. Does this? I don't see the connection between pre-allocation of buffers and communication. So maybe that's why I'm asking this question. What's the connection there?
Okay, so what we are actually doing, the pre-allocation of the buffers, basically get rid of all these mallocs and even on CUDA devices, CUDA malloc, that all kills you, right? So what we are basically doing, we are gauging the amount of pre-allocation from the while the program is running. So we are basically trying to over-allocate and adapt this over-allocation process as the simulation is going. If we would not do that, we would just be basically killed and in our communication routine, because that's where we do the allocation. So I think it's I should rephrase that a little bit. We do everything in this particle receive or particle send, and especially the particle send, if that would be if that one would always allocate the buffers, then you would see in this picture, if we can use already pre-allocated memory, basically this one goes down to 5%. Does that answer the question?
So the particle sends are sending particles between GPUs and CPU?
Yes.
Okay.
I mean, in principle, between the domains, right? Usually, these domains at the moment we have one GPU per MPI rank, right? So usually a domain is owned by an MPI rank. So you basically send it off to your neighboring GPU. Yes.
Thanks for the explanation.
Sure.
Do we have other questions? All right, I'm going to take the opportunity and ask my own question, because Andreas, I'm not from the Accelerator Society. From where I come from, a natural question that I would have is the validation against experiments with the modeling effort. Is that ever a practice in the accelerator field? Is that ever planned or considered in your field?
Yeah, of course, right? I mean, the one experiment is this one, right? I mean, we usually start. I mean, so for the solver, for example, right, you can do Landau damping, where you basically have your growth rates and everything. You can do that, and this is a real This is a real experiment where they basically measure a projection of the configuration space in Z, and they can measure the energy spread in the beam. So these are measurements, and so for example, with the Wiggler in, so that's the green curve, and the red, that's the simulation. I'm sorry, the experiment is red. And that is an honest and hard test case. We have others. We have other test cases. That is a very specific one because it needs Coulomb interaction plus radiation. So we have another test case done at LCLS where we only have radiation. So yes, we have different sorts of test cases on real machine, but also on more theoretical, even in some cases, analytic results.
Mm-hmm. Great to know. Thank you.
Welcome. So, and I mean, for the code, I mean, there is a whole what you would expect these days, that there is a whole I think we are running regression tests and module tests all over. If you put something in the master, roughly 300 tests will be executed during night on a GPU and CPU. Yeah, you have the whole testing in place.
Mm-hmm.
Just to basically do a quality assurance. Yes.
Yeah, got it. James?
Yeah, hi, Andreas. Thank you for a very interesting talk. So I have a question about that you had some very interesting scaling results, some very impressive scaling results. And I was wondering if you could say anything about like the single node performance when you use a single GPU or a single node. Do you have any idea of how efficient that is? So how well the hardware is being used? And
okay, short answer, no. No. So Sri, he was a former Marie Curie fellow. He just got permanent at Jülich. He did all this type of thing. He could tell you a lot about that. So you will find that paper on the archive. This is that one here, right? You can find it on the archive. Shoot him an email. He can tell you. I don't know that. In principle, as good as Cocos is, right? I'll put it that way, right? I mean, as good as. I mean, this is basically delegated to Cocos, right? If I do my integration, I have a Cocos 4, a parallel 4, whatever they call it, and that's it, right? So the only thing, and that is probably a little bit influences single particle performance as well, is single node performance is of course this type of buffer allocation. If even on one GPU, if I do a lot of alloc and dealloc, things will just stall, right? That will not work. So that's definitely a thing. And then I think from the expression template, there is not. I mean, this is, if you can compile that in one single Cocos kernel, and if the Cocos folks are doing a good job, I mean, then you are, well, then I can do anything, right? But this has also to do with probably as a computational scientist, you have always these three hats. And when I talk to a computer scientist, I know nothing. And then I talk to a physicist, and I also don't know anything. I talk to a numerical guy, and I say, okay, where I am, right? So I'm also not so interested in that, to be very honest. But three would know. Okay, so
well, thank you very much for the answer. Yeah, thank you.
Great. Since we're at 11 o'clock, I would like to call it a session for today.
All right. Okay.
Thank you, everyone, for joining. Thank you, Andreas, for the fantastic talk.
You're welcome.
Yeah.
Have a wonderful day.
Yeah, we will release you for dinner. You must be very hungry.
Thanks. Yeah, I'm hungry now. Yeah. Okay.
All right. Nice to see you.
Bye.
Yeah.
Nice
Bye.
to see you too. Bye.